Hello all. In the previous video, we had learned how to check the static property or the causal property of an LTI system by observing the impulse response. And we concluded that for a continuous time system, if the impulse response h of t is of the form c into delta of t, then the system is said to be static or memoryless. If it is not of this form, then the system is said to have memory. And if h of t is equal to 0 for t less than 0, then the system is said to be causal. If it doesn't satisfy this condition, the system is said to be non-causal. Similarly, for a discrete time system, we said that if h of n is of the form of c into delta of n, then the system is said to be static. And if h of n is equal to 0 for n less than 0, the system is said to be causal. In today's video, the objective of this video is to know when can we say that the system is stable by observing the impulse response of the system. Again, I have taken the same equation for a discrete time system, that is equation for convolution sum. Y of n is equal to summation k is equal to minus infinity to plus infinity h of k into x of n minus k. Before that, let me tell you what is the definition for stability under input-output relationship. If the input is bounded, and then if I get a bounded output from a system, then the system is said to be stable. So bounded input gives an bounded output for a stable system. That is the condition. Now let us try to obtain from the impulse response how can we derive the condition. Now applying the magnitude on the above equation, I can write magnitude of y of n is equal to magnitude of summation k is equal to minus infinity to plus infinity h of k into x of n minus k. Okay, now we know that the magnitude of sum of two numbers, so magnitude of sum of two numbers is always less than or equal to sum of their individual magnitudes. Sum of the individual magnitudes. So applying this condition on the above equation, I can write magnitude of y of n is less than or equal to summation k is equal to minus infinity to plus infinity magnitude of h of k into x of n minus k. Further, we also know that the magnitude of product of two numbers is always equal to the product of their magnitudes, that is product magnitude of A into magnitude of B. Applying this condition, I can write the magnitude of y of n is less than or equal to summation k is equal to minus infinity to plus infinity magnitude of h of k into magnitude of x of n minus k. Now let us assume that I have a bounded input, that is the magnitude of x of n is less than or equal to some finite quantity, obviously, which is less than infinity. If that is the case, then shifting doesn't cause the change in the magnitude, and hence the magnitude of x of n minus k will also be less than or equal to mx, which is less than infinity. Using this condition in the above equation, I can rewrite the equation as magnitude of y of n is less than or equal to summation k is equal to minus infinity to plus infinity magnitude of h of k into magnitude of x of n minus k. Now it is mx. Now since this is independent of k, which is a finite quantity, which is a constant, I can take it out and I can write it as magnitude of y of n is less than or equal to mx into summation k is equal to minus infinity to plus infinity magnitude of h of k. Now Now by observing this equation, we can know that the output will also be bounded provided the summation k is equal to minus infinity to plus infinity, magnitude of h of k is a finite quantity. Now this has to be a finite quantity. That means what? Summation k is equal to minus infinity to plus infinity, magnitude of h of k should be less than infinity. K is just a dummy variable. In general, summation k is equal to n is equal to minus infinity to plus infinity, magnitude of h of n. If it is less than infinity, then the system is said to be absolutely stable, because only this condition will ensure that the this quantity is finite, mx is finite, and then y of n will also be a finite quantity. That is, a bounded input is giving a bounded output, provided the impulse response of the system is absolutely summable. It should be absolutely summable. That means what? If I add all the terms, that is h of 0, h of 1, h of 2 and so on, or h of minus 1, h of minus 2, whatever it is, all those terms if I add, it should give me a finite quantity. That is why when it is absolutely summable, then an LTI system is said to be absolutely stable. Similarly, we can obtain a condition for a continuous time system if the impulse response of a continuous time system is absolutely integrable. If I can integrate it, say t is equal to minus infinity to plus infinity, magnitude of h of t. If I integrate the impulse response of the continuous time LTI system, and if I get a finite quantity which is absolutely integrable, then we say that system is stable. So it should be absolutely integrable. It should be absolutely integrable. So if it is integrable, okay, then the system is said to be stable. So this is the condition for uh, uh, discrete time system. Okay, it should be absolutely summable, and it should be absolutely integrable for a continuous time system. Only then we say that the system is stable. Okay, when can we say the system is integrable? Let us invertible. So under what condition the system is said to be invertible? Okay, to that, let us see that, say, let me consider a continuous time system. Let x of t be an input to an LTI system whose impulse response is given by h of t, and I am getting the output of the LTI system as y of t. Now this y of t is in turn given as an input, say, because the objective is to recover the input from the output, that is to recover x of t from y of t. Suppose I have another system whose impulse response is, say, h inverse of t, and I'm giving the input to this system is y of t, and if I get back the x of t, then we say that system 1 is invertible and system 2 is the inverse of system 1. Okay, now let us obtain the mathematical condition for this. So from the first arrangement, y of t is equal to h of t convolve with x of t. Let me call it as an equation 1. And for the second condition, x of t is equal to h inverse of t convolve with y of t. Okay, equation 2. Now substituting equation 1 in 2, if I substitute equation 1 in equation 2, then x of t is equal to h inverse of t convolve with, so in place of y of t I am writing h of t convolve with x of t. Okay, now using the associative property, I can combine this and this, and I can rewrite the equation as I can rewrite the equation as, so H inverse of T convolve with H of T convolve with X of T. If you observe, left hand side is X of T and right hand side of this equation. We know that identity property of the system, whenever X of T is convolved with delta of T, I can get back my signal X of T. Now, from the above equation, we can say that whenever H inverse of T is convolved with H of T, if it is equal to delta of T, only then I can get back the input. That is, the condition is, if H inverse of T convolve with H of T, if it is equal to delta of T, then the system is invertible. And similarly, for a discrete time system, we can obtain the condition as, when H inverse of T is for discrete time system, and H inverse of N is convolved with H of N, which is equal to delta of N, then we say that system is invertible, where H of N represents the impulse response of the system 1 or the original system, and H inverse of N represents the impulse response of the inverse system. Now, in this block diagram, we are trying to get back the input from the output. This is also called as deconvolution. That is, the process of getting back the input from the output is called as deconvolution. Okay, so it is called as deconvolution. Okay, so let us summarize. So we have from these two videos we have concluded that by observing the impulse response of the system, we can say whether the system is static or dynamic, causal or non-causal, stable or unstable, invertible or non-invertible. Thank you.